Welcome back. Today we are looking into the architectures of DSP. One of the biggest issue in executing the DSP algorithms is the transfer of information from and to the memory. This information includes data as well as instructions. Data are the samples from the input signal to the filter coefficients, which means that it includes the input as well as the filter coefficients. And the instructions are the program instructions, which is a binary coded sequence, and that sequence decide which operation has to perform. For example, if we want to multiply or add two numbers, we have to fetch three binary values from the memory. The three numbers include two are the numbers, that is the input as well as the filter coefficient, and the other is which program has to execute it, that is the program instruction. For executing the DSP algorithm, there are three architectures describing this. They are von Neumann architecture, Harvard architecture, and Super Harvard architecture. Coming to von Neumann architecture, the von Neumann architecture contains a single memory and a single bus for transferring data into and out of the central processing unit. Multiplying two numbers requires at least three clock cycles, one to transfer each of the three numbers over the bus to the to the CPU from the memory. Here we do not count the time or the clock cycle to transfer the result back to memory, because there is an assumption that the result after the program execution can be stored or can be remained in the CPU itself for the additional processing. Von Neumann design is quite satisfactory to execute all the required tasks in serial. The other architectures are used when we require the fast processing or we are willing to pay the price for their increased complexity. And this leads to the another two architectures such as Harvard architecture as well as Super Harvard architecture. So in von Neumann architecture, the processing an operation is very slow, but the advantage is that it has less complex. Coming to the Harvard architecture, the Harvard insisted separate memories for the data as well as for the program instructions with the separate buses for each. Since the buses operate independently, program instructions and data can be fetched at the same time. This improves the speed or when compared to the single bus system or the single bus design, that is the von Neumann architecture. One of the disadvantages of the Harvard architecture is that the data memory bus is busier than the program memory bus. For example, we are multiplying two numbers. So the two binary values must be passed over the data memory bus, while only one binary value is passed by over the program memory bus. To improve such a situation, the subsequent stage within the architecture with a notable superpower structure has implemented. So there is an improvement from the Harvard architecture to the super Harvard architecture. To improve the Harvard architecture, we have to relocate the part of the data to the program memory. Okay. For an instance, we can place the filter coefficients in the program memory, while the other data, that is the input data, can be passed over the data memory bus through the data memory by the input output controllers. So since the program memory is allocated with the uh, datas, that is the filter coefficients, this memory is able to handle the instructions as well as the data. So this reallocated data is also known as the secondary data. So if the input is coming from the data memory, at the same time the program memory will transfer the filter coefficients. There is another advantage or another feature that the instructions can be stored inside the CPU within a small memory, that is the instruction cache. So a single clock cycle is required to operate uh, one instruction, whereas in Harvard and Super Harvard, Harvard and von Neumann architecture, it requires two clock cycles and three clock cycles respectively. These are I have explained, and next coming to uh, the Super Harvard architecture is also known as shark architecture. So this is the typical structure for the shark architecture. Here, there is an I/O controller. The signals, that is the input signals, is enter and the output signals will access the system through this I/O controller. This I/O controller provides both serial and parallel communication ports. These are used for extremely high speed connections. In Super Harvard architecture, a dedicated hardware that allows the data stream to be transferred directly into the memory without having the pass without having passing through the data registers, and this concept is known as direct memory access, abbreviated as DMA. The main buses, that is the program memory bus and the data memory bus, are also accessible from the outside chip, providing an additional interface to off-chip memory and peripherals. The overriding goal is to move the data in, perform the operation or the perform the math, and move the data out before the next sample is available. Since there is analog to digital and digital to analog converters, mixed signals can be processed using this architecture. There is a block for DM data address generator which controls the address sent to the program and data memory, specifies which information is to be read or write. Some DSP algorithms are carried out in stages. Multiple stages requires multiple buffers for the fastest operation. DAGs are configured to generate bit reversed sequence to perform circular buffers used in the part of FFT algorithms. The data register section can hold intermediate calculation, prepare the data for the processor, serve as a buffer for data transfer, hold flags for the program control, and so on. These registers can also be used to control loops and counters. Math processing is broken into three sections such as multiplier, arithmetic and logical unit, a shifter, that's a parallel shifter. The multiplier takes the values from two registers, multiplies them and places the result into the another register. The ALU performs addition, subtraction, absolute value, logical operations such as and, or, not, XOR, like that. Conversion between fixed point and floating point formats, similar functions. The multiplier and the ALU can be used in parallel. Accumulator is built into the multiplier to reduce the round of error associated with them. Another interesting feature is the use of shadow registers for old CPUs. Duplicate registers can be switched with their counterparts in a single clock cycle. So it can have the feature of fast context switching and having the ability to handle interrupts quickly. Thank you.